Okay. Well, thank you for the invitation. Today I'll be talking about realizing tropical curves via mirror symmetry. This is some work which is comes out of my thesis, and hopefully there'll be a preprint on this going up in the next week or two related to some of the stuff I'll be talking about today. For those of you who weren't around for the pre-talk, mirror symmetry is a conjecture relationship between algebraic geometry and symplectic geometry via a third kind of geometry, which is affine or tropical geometry. So for this talk, the letter A will always refer to symplectic geometry. The letter B will refer to complex or algebraic geometry. And I apologize if I use the word algebraic geometry and complex geometry interchangeably. I really mean algebraic geometry, but I grew up a differential geometer, so that's where I get that language from. So XA will be symplectic space, XB will be some kind of algebraic space, and Q will always be an affine space. A space built from charts that look like R to the n with transition functions living in SLN. At the beginning of the talk, I'm going to focus a little bit more on the space XB. So I'm not actually going to be working with complex spaces. I'm going to be working with rigid analytic spaces during this talk. And so let me give a little bit of a primer to the notation that I'm going to use. So all the spaces that I'm concerned about on the XB side are going to be rigid analytic spaces with coefficients in this field called the Novikov field. So this field is denoted by lambda, and it consists of formal power series. So it's a sum over some index I of a to the I times t to the lambda I. Here t is just a formal parameter, and the ai are supposed to live in C. And the lambda I have to satisfy this relation, which is that the limit as I goes to infinity of lambda I goes to infinity, and the lambda I are real numbers. So think formal power series, except instead of using integer coefficients, I allow myself to use, integer exponents, I allow myself to use real valued exponents. And the kind of convergence property that I require is that the exponents go out to infinity over time. And this is going to make it so I have a well-defined product and so forth. And the fact that the exponents are allowed to take a negative value means I'm a field. The fact that the exponents have to limit to infinity tells me that there is a minimal negative exponent. So this comes with a valuation, which is the valuation of some element of this guy is the lambda I, which is smallest, so it's the minimum of these lambda i's, such that ai is not equal to 0. And if no such thing exists, then we'll say that the valuation of 0 is infinity. So this valuation takes values in R union infinity, and it tells me the smallest non-vanishing exponent which occurs in this expansion. The space which I'm going to be interested in, XB, is going to be an algebraic torus. So XB is the space lambda star to the n. So these are all of the invertible elements. I'll give this coordinates. Z1 ... Zn. So this is some fancy algebraic torus. Now, associated to XB, there is a process called tropicalization, which takes a subvariety or a set of XB and produces some subset of the plane. So I have at map the B tropicalization map from XB to Rn, And it's very simple. All it does is it takes the coordinates z1 through zn and sends them to the valuation of z1 ... the valuation of zn. Right. So because here I'm working on the algebraic torus, all of these valuations are going to wind up in Rn instead of winding up in the extended line, Rn union infinity. Now, this tropicalization map is a little bit amazing. So there's a theorem due to Groves and Bieri originally, but it's been extended in various different contexts with various different assumptions, which states roughly that given yb inside of xb subvariety, the tropicalization of yb, which is just defined to be equal to the image, well, it's a set of points trop y such that y is in yb, is a polyhedral complex of Rn, where so a union of convex polytopes. Okay, and maybe I can even say union of convex rational polytopes. So maybe like the most baby example that I could look at is if I looked at like z comma 0 inside of lambda star squared, so just the coordinate axis, then the tropicalization of y would be the line q comma 0 inside of R2. Now, the remarkable thing about this was like in the previous talk, we kind of explained how going from lines in R2 to subvarieties of lambda star 2 was kind of a natural thing to do. But this gives you kind of a reverse process where you can start with any subvariety of yb and then produce this kind of combinatorial object, the tropicalization of it. So let me give an example of how this kind of works out in practice. So here, the example that I'm looking at is yb, which is the line inside of the algebraic torus. So this is 1 plus z1 plus z2 is equal to 0 inside of lambda star squared. And the claim is that the tropicalization of this thing is just the union of these three lines over here. So you get this very rigid object. And why does the projection of a point y inside of yb have to lie in the union of these three lines? Well, if it was to lie in this portion over here, then the valuation of the z1 coordinate would be bigger than the valuation of the z2 coordinate, or is 1. And therefore, the valuation of 1 plus z1 plus z2 would have to be the valuation of z1. So over in this region, the valuation of z1 is equal to the valuation of 1 plus z1 plus z2, which is not equal to the valuation of 0, which is infinity. So there can be no points of yb which lie in this kind of right third of the plane. Similarly, there are no points of yb that lie in the top third of the plane because that's where the valuation of z2 dominates. And there's no points that lie in the bottom third of the plane because that's where the valuation of 1 dominates. So maybe one way to think about these kind of tropical objects is, at least in the case of hypersurfaces, every hypersurface is cut out by some kind of polynomial or power series. And what this is doing is it's just kind of recording what regions of the plane give the leading order term dominations of that power series. And then you know that the actual curve itself has to live in the complement of those regions. So you can kind of imagine how this type of proof by Groves-Bieri works in general, at least for the case of hypersurfaces. In fact, these tropical objects that you give that you obtain from this process have a lot more structure. You'll notice that if I look at this vertex over here, that these three edges that emanate from the vertex point in the -1, 0, 0, -1, and 1, 1 directions, and that the sum of those three directions is 0. This is kind of a general property of the tropical objects that you study, but I'm not going to need that for this talk. Okay. So, or maybe actually I will need it. Okay, so one of the simplest types of tropical objects that you can study are tropical curves. So what are these? These are a tropical curve is a piecewise linear graph in Rn such that at every edge we have a primitive Zn vector describing the direction of the edge, and at each vertex, the sum over all edges which contain that vertex have the sum of these little vectors being equal to 0. Okay, so in the previous example that I gave, this was the fact that at this vertex, at this edge over here, we had this 1, 1 direction. At this vertex over here, we had this 0, -1 direction. And at this vertex over here, we had this -1, 0 direction. And that the sum of those three directions is 0. The tropicalization process will take a curve and it produces a tropical curve for you. The realization process is the reverse of this. So ask the question, for given tropical curve V inside of Q, does there exist YV inside of XB such that the tropicalization of YB, of YV is equal to V. So can you find something which has a set tropicalization? Now, why would this be kind of an extremely desirable thing to happen? Well, you could imagine that you had some problem where you're trying to count curves inside of a variety, kind of historically interesting and difficult problem to do. And this states, well, instead of counting curves inside of a variety, if you have this B realizability condition, then you can instead just count tropical curves inside of the tropical subvariety, understand the relationship between these two objects, and reduce your entire problem to combinatorics somehow. Answer to this question is not always. There are known examples of tropical curves which are not realizable. They don't lift. So then the next question you ask is, for which tropical curves can you build a lift? So this is the realizability problem. Okay, so having described the realizability problem, what is the main idea of this talk? So in the previous talk, we talked about how given an affine manifold Q, we can produce an algebraic space XB. So in this case, it'll be this Novikov algebraic torus. We described how we can build a symplectic space XA such that XA and XB both have these fibrations over Q. And I've just described that there's an interesting relation, which is when I start with Y inside of this, then we have a tropicalization problem, trop B, which winds me up with something V inside of here, which is a tropical subvariety. And there's this question, which is can I realize this thing? And the answer is not always. Now, there's an overarching framework for a relation between these two spaces, mirror symmetry, which says that Lagrangian submanifolds inside of XA are supposed to be related to complex, or I should say algebraic subvarieties of XB. And so you can kind of ask the mirror problem starting with V. Well, starting with a Lagrangian submanifold, is there a tropicalization map, trop A, and can I realize? Now, I think historically, this relationship between tropicalizations and realizations was the inspiration for deducing the existence of this top arrow over here. So there was some kind of dream proof where you start with any Lagrangian submanifold, you tropicalize it, and then you lift the realization, and then that gives you this top arrow. In practice, this is actually not how mirror symmetry is done. There are lots of examples where we know the existence of this arrow at the top without knowing knowing anything about what lies underneath here. So the bottom half is kind of a useful heuristic for understanding why mirror symmetry should work. But in practice, the way that we match up XA and XB is by using some kind of very heavy homological algebra. So the idea of this talk is to solve this realizability problem. Instead, start with your tropical curve, realize it this way, and then push across using homological mirror symmetry to get your algebraic subvariety. And the question is this an easier process to do than just realizing it by hand in the first place? And what are the advantages and what are the kind of potential difficulties? Okay. In order to do this, first, I think we have to understand this tropicalization A map a little bit better. Okay, so there's a naive approach to A tropicalization, which is the following. So we could define, first attempt. Actually, maybe before I go on to the actual meat of the talk, is there any questions about this kind of the outline or the strategy that we're going to employ?
Nothing on the chat for now, so.
Okay, great. In that case, I'll continue. Yeah, so the first approach is kind of naive attempt to atropicalization as well. Given L inside of XA, we'll just look at pi A of L. Okay, so this is just look at the set in Rn that I obtained under this projection. Okay, so this is very rarely tropical. 2, given L and L prime, which are Hamiltonian isotopic, which is like a useful equivalence preserving symplectic geometry. Pi A of L is not equal to pi A of L prime. So just taking something inside of C star to the n, which is a Lagrangian submanifold, and projecting it to Rn under this map pi A, which sends the coordinates of C star to the n, Z A1 dot 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 Z A n maps to log absolute value ZAI, is not a good tropicalization process. It very rarely produces tropical things, and under kind of the type of equivalence between Lagrangian submanifolds, which preserve symplectic geometry, you get different tropicalizations of the same object. So the central problem over here is that symplectic geometry is very flexible. I can take a Lagrangian submanifold and I can find, a whole bunch of other Lagrangian submanifolds which are close by to it, which are supposed to be exactly the same. So on first glance, the kind of the rigidity that allows you to maybe expect a relationship between algebraic geometry and tropical geometry simply doesn't exist on the symplectic geometry side. The workaround to this is to introduce some rigidity into symplectic geometry. And this comes in the form of an object called Floer cohomology, which is a type of generalization of the intersection between two Lagrangian submanifolds. So this was introduced by Floer to solve this problem called the displacement problem. I'm going to just give a definition of it over here. So given Lagrangian submanifolds L1 and L2, satisfying some conditions, which I will call star, and I will return to later, the Lagrangian intersection Floer cohomology is a chain complex. It's generated on the intersection points between my Lagrangian submanifolds. So as a chain complex, it's a free graded Novikov chain complex generated on the intersection points. And the differential between two intersection points is given by a structure coefficient, which counts the holomorphic strips with boundary on one Lagrangian, a boundary on the other Lagrangian, going from the first intersection point to the second intersection point. This is kind of a strange thing to see out of the blue. So I want to look at some examples which will kind of be prototypical for what we're doing. So let's do some example computations. So the first example that I want to look at is the Lagrangian, which is S1, and another Lagrangian, which is S1, which are these two circles on the right-hand side over here, inside of C star. And in order to have a well-defined theory, I need to have intersection points between my Lagrangians. So I need to take one Lagrangian and kind of push it off a little bit. So I have intersection points. Okay, so then I'll have two intersection points between these guys. I'll have a guy in front, which I'll call E, a guy in back, which I'll call X. So right now my chain complex has two generators, one in degree, you can check that one of these will be in degree 0. One of these will be in degree 1. And then the differential is supposed to count the holomorphic strips which travel from the first intersection point. So you can see that there's on this left, that highlighter is way too thick. On the left-hand side, there's a little strip that goes from E to X. And on the right-hand side, there's another strip that goes from E to X.
Okay, so we have these two strips. One of them a plus strip, one of them a minus strip. They cancel out. The differential ends up being 0. This thing actually just ends up being the same as the chain complex of just chains on S1. So you got a generator in degree 0 and degree 1. Okay, a second example that you might look at is the intersection between S1 and R. Okay, so these intersect at a single point. Let's call it E. Okay, so this chain complex has only one generator in degree 0. There therefore cannot be any other differential, and that's the entire story there. Like you just get a vector space. Okay. Okay. So what are the upshots of using Lagrangian intersection Floer cohomology? Well, the upshot is that the homology of this theory L1, L2 is independent of Hamiltonian isotopy. So if I replace L1 and L2 with things which are Hamiltonian isotopic to them, I get the same thing. So this takes a symplectic geometry, which apparently is kind of very flexible and adds some rigidity to it. Try as you might, this says, for instance, that you cannot take a circle and displace it from itself by using one of these Hamiltonian isotopies, because whenever you try pushing it off of itself, you will leave the Floer theory unchanged, and therefore there has to be an intersection somewhere. Okay, let's try one more example computation, which is a little bit trickier. So again, I'm going to look at C star squared over R2, given by the projection which sends Z1A, Z2A to log of the absolute values of the Zi. Right. Now, there are two Lagrangians which I want to look at. So the first one is a fiber of this pi, FQ. And the second one is I'm going to start with V, a one-dimensional subspace of like a line inside of R2. And I'll look at the construction from the first talk, which is taking the conormal torus to it. So this was a construction that started with any affine submanifold of R2 and produces a Lagrangian submanifold upstairs. So to help visualize this, I've drawn two pictures. The first is a picture on the left, which is what everything looks like when it's projected to the R2 base. So in the R2 base, I have this Q, which is a point. I have this V, which is a line. I want the point to travel through the line. And so it looks like kind of in the R2 base projection that they intersect. The other picture which I can draw is I could draw the projection from XA to FQ, which takes Z1A, Z2A to the arguments of each of the coordinates. And in this picture, okay, Q, well, FQ will be kind of everything in this picture, it's the whole fiber. And the other thing that you see is that the lift of this V gets taken to kind of the perpendicular direction, because this is a conormal construction. Now, this is just to kind of get some intuition for what the geometry is like. In practice, actually, to compute CF LV FQ, I use the fact that this picture over here is just the product of these two pictures on the left-hand side. So C star squared is the product of C and C star. FQ is the product of S1 and S1. And this LV is, well, in one direction it looks like the R component Lagrangian, and the other direction it looks like the S1 component Lagrangian. Okay, so this is actually equal to CF S1 S1 tensor product CF S1 R. Okay, this guy was just lambda, and this guy was chains on S1. Okay, so for things that kind of come from this product decomposition, we can compute the Lagrangian intersection of Floer cohomology pretty easily. There's a Kunith type formula for computing these things. For this talk, I'll need one generalization of this theory, which is a little bit technical, which is that the theory can be generalized to look at Lagrangian submanifolds, which also have these unitary local systems on them. So a unitary local system is going to be a choice of a flat flat U lambda vector bundle. When one computes the differential, or one looks at this chain complex, well, as a vector space, it's again given by the sum over all intersections between L1 and L2 of lambda generated by X. But the differential now, which previously just counted holomorphic strips, counts something a little bit different. So if I have a strip traveling between X and Y 2 points, then I take the parallel transport map along the boundary of the strip, and kind of I get some contribution from the parallel transport map from the boundary of the strip on the first Lagrangian L1, and I get some contribution from the parallel transport map along the second boundary of the strip, and I get a contribution from L2, and then I take the differential of X against Y to be equal to, well, the sum over all such strips of not just the count, but the count weighted by the parallel transport maps. So this assigns now not just kind of a number to each strip, but it assigns some kind of unitary Novikov element to each strip. This is kind of an odd generalization to look at, but it's natural from the following observation, which is that given C star to the n, Rn, and we had this space xb to Rn, the points, well, we have a bijection between the points on xb and the Lagrangian torus fibers of pi fq, additionally equipped with a U1 local system. Okay, so let's kind of unwind what this is saying. If I look at like xb over Rn, there are many points that have the same Novikov valuation. Right? There's a whole bunch of them because the valuation is only recording the lowest order term of the power series and the expansion of that point. But all such points differ by a unitary Novikov element. And what this is saying is, well, if I look at my symplectic manifold A over Rn, then associated to every point in here, there's only one Lagrangian torus that lives over it. And in order to make sure that I have kind of enough Lagrangian-like objects to match up with the points inside of this left-hand side, I'm going to look at not just Lagrangians, but Lagrangians equipped with unitary local systems. So this is kind of one way where you can see that the spaces xb and xa are related to each other. You can think of xb as being the moduli space of Lagrangian torus on xa equipped with unitary local systems. The real mirror symmetry statement that makes all of this tick is that if you have a Lagrangian L inside of XA satisfying the condition star, so it has to have well-defined flow cohomology, then there exists a sheaf F L on XB such that the sheaf hom between FL and the skyscraper sheaf of a point is equal to the Lagrangian intersection flow homology between L and one of these fibers under the bijection of points in the left-hand side with fibers equipped with unitary local systems on the right-hand side. Okay, so this theorem due to Abu Zaid, called the family Floer theorem, is a very heavy piece of symplectic geometry. And it provides basically a method for saying, well, on the right-hand side, I have a whole bunch of Lagrangians, which I presuppose are the mirror objects to points. Now, from the data of a bunch of Lagrangians, I get the data of a bunch of Lagrangian intersection flow cohomologies, and I can show that I can assemble that data completely into a sheaf. So at the very beginning of the talk, when I said that there were kind of modern methods in symplectic geometry to prove mirror symmetry which didn't travel through the tropicalization, this is what I mean. So this theorem just takes as the input some Lagrangian submanifold and produces as the output for you some sheaf. Granted, the Lagrangians have to satisfy this condition, which I haven't gone into yet. Okay, so with this theorem, we now have kind of the following better candidate for what atropicalization should be. So given a Lagrangian submanifold L inside of XA satisfying condition star, then we define the tropicalization of L to be the set of Q in Rn such that there exists lambda a local system so that HFL FQ lambda is not equal to 0. So this is mirror to the set of points in the support of FL with B tropicalization equal to Q. So I look at all these Lagrangian fibers. I find out which ones intersect. Sorry, I look at all of these Lagrangian torus fibers. I compute their Lagrangian intersection flow cohomologies against L, and I see where do they not vanish, and I define that to be the tropicalization. There's a kind of easy thing to see, which is that the tropicalization of L is a subset of the projection of L down to the base. And the proof is, so suppose that Q is not in the projection of L down to the base, then FQ, the Lagrangian torus fiber, which is the fiber over Q, has no intersection with L. So CFL FQ is 0. So this is really saying that this tropicalization map that we've defined over here is a refinement of just the naive tropicalization where you just project down to the base and forget everything. Okay, so now we have a tropicalization method on the A side. Now we should talk a little bit about the realization problem. So can I take a Lagrangian submanifold, lift it up, or sorry, can I take a tropical curve, lift it up to a Lagrangian submanifold? So what does it mean to have a tropical Lagrangian lift of a tropical submanifold? Definition: a Lagrangian L inside of XA is a lift of a tropical curve V inside of Q if at every edge of V, the Lagrangian looks like the conormal construction at that edge. Okay, so kind of the picture to have in mind is I start with some tropical curve in the base, and then when I want to lift it to a Lagrangian inside of C star squared, I require that over the edges, I do the conormal lifting construction. So that's the thing that we covered in the pre-talk, which said that when I had a linear subspace, I could pretty easily build a Lagrangian submanifold associated to it. Okay, and then there's a worry about what you do in the middle. And this definition just says, do whatever you want in the middle. Just find some Lagrangian that goes in over there. Don't worry what it is. A theorem, which is kind of discovered at the same time by many different people, Matesi, Diego Matesi and Mikhalkin, and myself, and it was probably kind of known to symplectic geometers before this was worked out, was every V has a lift, LV. So if you start with any Lagrangian or any tropical curve, you can build this Lagrangian submanifold. And essentially, the reason that you can do this is because Lagrangians are so flexible. You know, if I start with some local model for how to build the lift, then because Lagrangian submanifolds are very flexible and they're very easy to glue together, you can build it for kind of anything which is glued out of them. And since tropical curves are all built out of these very simple pieces, you can build out anything. In fact, Matesi, Mikhalkin, and myself in our papers prove like actually that much wider variety of tropical objects can be lifted up. So any tropical subvariety, which is complete intersection, or every tropical hypersurface, or you know, various classes of tropical objects all have Lagrangian lifts. And this is contradictory kind of to what you see on the A side, where there's a realizability problem. It is difficult to take a tropical curve and lift it to an algebraic object. And the key insight is that this lift is a very geometric thing, but not all the Lagrangians satisfy the condition star, which I've been leaving off for a while now. So they may not have well-defined Lagrangian intersection Flow-Orbital homology. This is kind of an overlooked point in symplectic geometry, which is that, or in mirror symmetry, which is usually stated that Lagrangian submanifolds are mirror to complex varieties. It's actually the Lagrangian submanifold satisfying some rather lengthy list of technical conditions are mirror to a complex of varieties. And checking these conditions is work. Okay, so our roadmap to A realizability now looks something like this. So start with V inside of Q. You can always lift it to LV inside of XA. Okay, now check the condition star. Then you get a Lagrangian, which is an object of the so-called Fukaya category, which is what this condition star says. Okay, and then you apply mirror symmetry due to Abu Zaid to build yourself a coherent sheaf on the mirror. Okay, and then you take support, and now you get something inside of XB. Okay, and then you check that when you tropicalize this, you wind up back where you started. So there's kind of a problem. Problem one is kind of checking that you satisfy the technical conditions. And then the second problem is that like this says that you build for you end up building some tropical object, but did you get like the right one out? You could have gotten some different tropical object out. Okay, so the theorem is that whenever LV satisfies condition star, then the above diagram commutes. Or you can say condition star implies B realizability. So recall that this B realizability was trying to build a lift on the algebraic side, and this says that you build a lift instead by going all the way to symplectic geometry, passing across and coming back. So the existence of this arrow is the existence of this check. Maybe I should say what is condition star. So condition star over the years has become kind of enlarged to contain a larger and larger set of symplectic manifolds. I started out with requiring that your Lagrangian submanifolds are exact, and then was upgraded to saying that the symplectic form vanishes on all disk classes with boundary on your Lagrangian, or got enhanced to L as what's a so-called monotone Lagrangian submanifold. And this finally got enhanced to L is unobstructed, which is to say that the A infinity curved A infinity algebra CFL constructed by Fukaya is homotopy equivalent to a non-curved one. There's an algebra that you can associate to every Lagrangian submanifold, this curved A infinity algebra. It's a chain it looks like a chain complex that comes with a differential, but the differential doesn't square to zero. And there's an algebraic obstruction to trying to make the differential square to zero. And if you can solve that algebraic disruption, then your Lagrangian is called unobstructed and it has a well-defined flow cohomology. These conditions are kind of topological and therefore somewhat easy to check. This condition is tricky to check. But we have some examples where we know how to do this. So maybe let me go through some example applications. Okay, so theorem. If L is inside of XA and dimension of XA, the real dimension is less than 4, equal to 4, then L is unobstructed. So this is a theorem that comes from symplectic geometry in general. Okay, and this implies that all curves, all tropical curves, and then Q equals 2 are realizable. In the case where Q is equal to R2, this is known. This was actually, I think, one of the starting points of this study of realizability and tropicalization in Mikhalkin's original work. For Q equal to T2, which is example where you'll end up building kind of the mirror to a billion, like where you end up building a billion varieties. For kind of algebraic realizability, this is some very recent work of Nishino from, I think, 21. And for kind of the analytic realizability, which is being handled over here because we're building mirrors to rigid analytic spaces, this is a new result. There's something about symplectic geometry which makes it like easy to prove that you can have kind of certain deformation arguments, which are kind of harder to see on the algebraic geometry side. In kind of some in work from my thesis, I prove that all tropical hypersurfaces have LV satisfying this condition star. Again, in the case of surfaces, or like in the case of Rn, this was something that was known. I think, probably even from before the work of Mikhalkin, you can just explicitly write down the tropical realization, but in general, it's kind of tricky. There's some kind of other applications that you can come up with. For instance, you can show that if V is a tropical curve of genus 0, then LV satisfies this condition star as well. So this was proven by Siebert and Nishino on the A side, so that every genus 0 tropical curve is realizable, is a kind of result which is known on the algebraic geometry side, but this gives kind of a proof that uses completely different methods, and again seems to generalize beyond the case of Rn. Okay, I will stop there because I'm out of time, but thank you for listening.